Hello and welcome back to another video for CS334. Today we're going to start bringing together a number of the pieces that we've been building up in terms of how a database system actually execute queries and talk about kind of the bigger picture models and how a database system might go about kind of connecting these different operations to each other. So I'm feeling a bit hungry, and I like a good peanut butter and jelly sandwich. So let's say that I want to consult the database of sandwich ingredients in order to write a query that's going to kind of optimize my peanut butter and jelly experience. So I might say I want to select a brand of peanut butter and a flavor of jelly from PB join J, and what I'm going to join them on is that their spread is the same. So like chunky peanut butter goes with jelly with stuff in it, and smooth peanut butter goes with smooth jelly. So we'll join them with PB spread equals J dot spread, and I definitely want a peanut butter and jelly sandwich where the jelly type is fruit, no Marmite, Vegemite, none of that stuff for me. And so given this this query, we can see it as we've seen the last few videos in query plan form, which we'll do as a tree. So at the top we have projection, getting the brand and flavor, and kind of input to that is our join, its condition, and feeding into this join are our two relations. So we are filtering out to get only fruit jellies. All right, so here's our query plan. And the first thing that I want to talk about is what's called the processing model. And this is, as I said, kind of how a database is actually going to go about executing the query plan. Things like kind of which direction are we doing this query plan in, how are we passing data between these operators. And this is what's known as the processing model. And there are three models that I want to talk about in this video. The first is going to be the Iterator Model. Then we'll talk about the Materialization Model. And last, the Vectorization Model. So up first, our Iterator Model. The Iterator Model is the most common model in database systems for row store database systems anyway, and it's also kind of the one that's kind of nice and simple to understand. So one thing I should say about the Iterator model is that it also, of course, has other names that people call it. When it comes to databases, there's never just one term. So this is also known as the volcano model or the pipeline model. The textbook will refer to it as a pipeline. Volcano comes from the research database system that was kind of originally implementing this model that their research paper referred to it as the volcano model. Their system, that's what their system was called. As usual with these sort of things, it just sort of stuck. But we'll call it the iterator model. I think that makes it kind of nice and clear what's going on. And the key idea here is that each of the operators in our system, each of the operators which compose a query plan, is going to implement a next method. So each of these operators have this API defined by the processing model, and the iterator model says, all right, each of these will have a next method that returns the next tuple that would be output by that operator. And then each of these operators is going to call next on its children to get the next tuples it should have as input to then operate on. And so let's put some actual pseudocode to this. So up here at the top, we have our projection for tuple in child.next. Then we will emit the projection of that tuple. And here I'm using emit like I have before to mean output, kind of send to whatever the next step is for the thing at the top of our query plan. That's like send to the actual output of the query. And then below that we have our join. And let's say this is going to do a hash join. And so the first thing that the hash join will need to do is to build the hash table for the outer relation. So for our tuple, I'll say T1 in the left child returned by next, we will put it into our hash table, and then after we built this hash table, we go through the tuples in the inner relation and probe the hash table to find the tuples that match for our join. So then for T2, in right.next, if we successfully probe our hash table with T2 and find a matching tuple, then we will emit T1 joined with T2. All right, so this is our kind of join node here. And fix this arrow. It needs to go there. All right, so then the last operator besides our two kind of input tables at the bottom is our select here. So let's put some pseudocode to that. For this, it's going to be similar to our projection, where we'll just iterate over the tuples coming in from our child. And if the predicate at this node is true, then we will emit that tuple. And then we'll actually have operators for our input tables down here. So and they're both going to be the same, where we just say for tuple in the table, emit the tuple. And similarly for J as well. So what this is going to do is that kind of first we'll start up at the top of our of our plan. We'll say for t in child.next. So this will call next on its child. And so then for t1 in left.next. And so it will go call next on its child. So each of these arrows is a call to next. So we call next on this child, and then its next method emits one tuple back up. And so then we'll have a tuple going back up. And this here is a single tuple in this iterator model, where our root node called next on its child, which called next on its child, which got back a tuple. We build a hash table. We keep calling next on the child, keep returning. Eventually, our next method returns some sort of marker, typically null, to indicate that there are no more tuples. And at that point, the join node knows that there are no more tuples coming from the left child, so this loop is complete. And then it calls next on its right child, which calls next on its child, which returns a tuple back up, which then emits some tuples back up to its node. So then our join would keep calling next on its child, which calls next on its child. And one thing that we want to try and do in this iterator model, and this is where this idea of a pipeline comes in, is that when we emit a tuple, we kind of want to do as much as we can with it all the way up before going back and getting another tuple. Because that way we can kind of make as much progress as possible in our query. And this is not always possible. For example, when we emit these tuples from our peanut butter table to the join operator, the join operator can't actually output tuples to its parent. It can't send them back up until the join is mostly or entirely complete, right? It needs to get all the tuples from the left to build that hash table before it can start finding potential matches and emitting join tuples. And so this join node here is what we would refer to as a pipeline breaker, meaning that we can't, tuples can't kind of one by one just kind of continue up from it. We actually have to, it blocks the pipeline, and we kind of have to get all the tuples in there before we can know what the result will be. Order by is another example of a pipeline breaker, because you need to have everything sorted before you can kind of output the first one. And subqueries are another example. In contrast, when we emit a tuple from the jelly table, and we can immediately apply our predicate that its type is fruit and emit it to the join. And so we can kind of continue that pipeline again until we hit the pipeline breaker of the join. One thing that works pretty nicely in this model is something like a limit. So if we added to our query, say limit 10, then what we could do is at the root node, we know that we only need 10 things, and then we can stop calling next. So we would, the pseudocode would change so that we would loop through we would loop through the results of child.next until we had gotten 10 back, and then we could just stop. And so that makes kind of something, implementing something like a limit quite straightforward. All right. So that's our iterator model. Now we'll move on to the materialization model. And the big difference in the materialization is that we're going to, instead of emitting tuples one by one. We're actually going to collect all the tuples that a particular operator will emit and then send them up all at once. So I'm going to clean up this diagram a bit, and then we'll walk through how that's going to work. All right, so the key thing that's going to change in this pseudocode for this materialization model is that we're actually going to have a buffer for all of our operators. So some empty list, something like that, to start out. And then instead of emitting a tuple one by one, we're going to add it to our output buffer. So all of these become out.add in our pseudocode. So now all of these operators are just in these loops. They're building up, they're filling up these output buffers with the tuples from that operator, and then out, once the loops are finished, it would all just return the output, meaning send the whole buffer up to the next operator. All right, so for this materialization model, then our root of our query plan is going to instead of implementing a next on each of the children, we're going to implement an output method. And we'll only need to call this output method once on each of our children instead of once for every tuple that we want to get at. So our root node will call output on its child. The join will call output on the left. This left node will loop through all the tuples in peanut butter, add them to its buffer, and then send the whole lot of them back up to the join. This will then call output on the right, which calls output on the jelly table. It fills up its buffer. We then iterate, we get that whole thing, iterate through all of it, adding the ones that pass the predicate to the output buffer for our selection, and then send that up to the join, which goes through all of them, building up a buffer of all the join tuples, which finally sends that back to the root. So one advantage of this is that we have many fewer function calls, right? Only one for each child rather than one for each tuple. And once we have processed a node, we never have to go back to it to get more data. We've collected everything there is to get from this, and we send it back up the query plan. So this is kind of a good fit for our OLTP workload, our online transaction processing. That's because our OLTP workload, if you remember, is kind of lots of updates, inserts, point queries that are like retrieving a specific user's account information, something like that. And so since in OLTP workloads, kind of each of these operators are typically going to be only dealing with a few tuples, then doing this materialization approach where we collect them all and send them up isn't going to kind of require tons of memory to hold these kind of large intermediate results, because we expect them to typically be small. And this is also good for in-memory databases. So our focus has been on disk-based database management systems. These are kind of the most common. They're very flexible, but there are specifically in-memory databases that don't use the disk at all, or at least not in the same way. And so for these in-memory ones, it's the case that the reading and writing from disk is no longer the bottleneck for performance. You're not doing that. Everything is in memory. Of course, if everything is in memory, you have less space to work with. But that means that if disk I/O is not the bottleneck, the number of function calls you're making may start to be a significant fraction, a significant impact on the performance of your database. And so in that case, this materialization model, which dramatically reduces the number of function calls, can reduce the overhead for executing the query plan. This is going to be bad for our OLAP workloads, our online analytics processing, because these tend to be queries that are looking at a large number of tuples, which means that these output buffers are going to be filling up with large amounts of data. And if these output buffers start having to kind of spill to disk, they get too big for memory and we have to start writing out pages of them to disk. Now we've introduced a whole bunch more disk I/O into our query plan that under the Iterator model would not have been there, because we're only moving one tuple at a time in that model. And so we would not want to design a database designed for OLAP would typically avoid something like the materialization model. So our third model now, the vectorization model, is sort of a hybrid of these previous two. So in our vectorization model, we're actually going to kind of go back to the world where we have a next method instead of an output as our operator API. But instead of next returning a single tuple, we're actually going to batch them up. And we're going to return kind of batches or small chunks of tuples with each call to next. So we're actually still going to have this output buffer in each of our query nodes. But what we're going to do is that once the output buffer will have some relatively small limit, and once it fills up with that limit, then we return that kind of batch of tuples for the return value for that call to next. So what this will look like is we'll be adding to our output operators, and then we'll say if the length of the output is greater than n, we'll emit that kind of chunk of output to the parent, and emit will also serve to clear out our output buffer, and then we'll start adding the next batch of tuples to it. And so this sort of logic of if the output buffer is bigger than some size n, we emit it to the next thing, that would appear in all these nodes. I don't really have space on the board to write this all out, but you can see it in the nodes, and I trust that you can imagine that this sort of, if our output buffer reaches a certain size, we'd have this inside the loop, then we emit that chunk to the next operator on our query plan. I'll trust that you can kind of visualize how that would go. And the couple advantages to this is this is a good model for OLAP, because if we have a query where we are expecting these operators to be scanning and outputting large amounts of tuples, Then by batching them, instead of one at a time, if we're doing 100 at a time, well, we have 100 times fewer calls to next that way. And so we can reduce overhead by doing this sort of batching of our outputs. And so sort of high-end analytics databases will typically support this sort of vectorization model. One hardware-related thing is that if we're compiling our query plan to low-level instructions, which a number of databases will do for performance reasons, this code can end up using what are called Simdi instructions, which are single instruction multiple data is what Simdi stands for, and these are single modern CPUs support these instructions that with a single instruction can operate on a vector, a kind of fixed length array of data at the same time. So you might be used to thinking of a CPU has an add instruction, and it can take like one value and add it to another, and there's going to be an equivalent Simdi instruction that can take a vector of 32 numbers and add it to another vector of 32 numbers as a single instruction. So these can be a really efficient way to work with these kind of chunks of data, and this vectorization model, by operating on these vectors, these batches of tuples, can take advantage of that and get performance benefits from it. So as I've explained all three of these models, something that I've talked about in each of these explanations is that we start at the root and it calls next on its child, which calls next on its children, and so on and so forth. And this is kind of this is what you would call a top to bottom, or the textbook calls this a demand-driven query execution, where our root node, we start at the top, the root node, it demands input from its child, which demands input from this child, and these kind of next calls go down into our tables, and then data propagates back up. So this is kind of a top to bottom approach. We also can have a query execution that goes the other way. A bottom to top or producer-driven model, where these nodes at the bottom, they are producing tuples and basically shoving them up the query plan. So our jelly table would produce tuples, and then it would insert them in an input buffer that our selection operator would have, and our selection operator would consume the tuples from its input buffer, and then pass them on to the join. And so there would no longer be the nodes would no longer be calling next on their children. They'd be calling pop or remove. They basically, on these input buffers, they'd be kind of waiting for there to be tuples in the input buffer and then consuming them. And this sort of, there's connecting these two would be a queue of the selection inserts and the join removes from. This sort of producer-consumer model is common across many different kinds of systems, software. You see a lot in networks. It shows up in operating systems. And indeed, it shows up in databases. So this bottom to top can be quite a bit more complex in terms of reasoning about the query plan. When you go from top to bottom, you sort of know everything that's going on because you've traversed the whole plan to get to the bottom. Whereas you go from bottom to top, there are now these like the coordination between the nodes is no longer like just a method call. It's these kind of producer consumer buffers. But what you get in exchange for this additional complexity is that you can achieve, in some cases, better parallelization with this bottom to top, where you can have kind of multiple nodes working separately on their own threads to push output up the query plan. And as in, it has a similar benefit to like the materialization, vectorization models, where we're doing fewer function calls if we're doing this bottom up instead of relying on these top down next calls to give output. And so top to bottom, far more common than bottom to top, but some systems do take this approach. All right, so this was all about the processing model, how a database system is going about and actually executing and connecting the portions of a query plan. The other main focus for today's video is what are called access methods. And we've talked about some of this already, but I kind of want to bring it together. And an access method is how are we actually getting the tuples in these tables here, these for loops here. Because in all the other nodes, we're calling next on the children. But in these nodes at the bottom, I just wrote for tuple in Jelly without saying, all right, how is it actually retrieving tuples on Jelly? And so that's what is called an access method, and that's what I'll talk about next. So when it comes to access methods, there are going to be two kinds that we'll look at. We have the trusty sequential scan, and then we have an index scan. And so these are kind of the two places that we might get our data from. We might go to the actual data files, the pages on disk for our database, and scan through the tuples in them. That's our sequential scan. We might have an index that has some or even all of the attributes that our query needs, and so we might scan the index in order to retrieve those values instead of needing to scan the full data sequentially. And of course, an index also, if it's something like a B+ tree, sorts the data according to some attributes, and so that can also be useful. But let's talk a little more about the sequential scan first. So this is going to maintain an internal cursor as it scans through. So it's like keeping track of where it is in the data files. And so in our, say, iterator model, the node at the bottom there, that for loop, is maintaining this cursor of where it is in the data file, so it knows which tuple to emit next when that method is called. And sequential scan seems like it might be a kind of this sort of just linear read everything. Might be kind of inefficient, but there are a number of things that we can do to make sequential scans more efficient. So one thing we might do is parallelize this sequential scan. If we have a lot of tuples to scan, well, they're separated into different pages, and so we could have multiple threads, each scanning various pages, and then kind of outputting the relevant tuples to some shared buffer. And particularly if our sequential scan involves some sort of filtering. So the way that I drew the query plan, we iterated through every tuple of J and then sent that to this selection selection operator, but you might also have a query plan where the two of these together is implemented as a sequential scan that does this filtering as it goes. So there, parallelization is helpful as well. Something that has come up before in various contexts is prefetching or buffering as much input as we can. So we're currently kind of, we have this cursor, we're reading through the page, and in the meantime, we also read in other pages that we're going to scan, sequentially scan through later on as part of this query, and so that when we finish scanning the page that we're currently on, the pages that we're going to scan next are already in memory, ready to go. And we saw with the sorting and join algorithms that kind of buffering a lot of input, this sort of same sort of prefetching idea is a good way to improve performance. So another thing that it was mentioned in the video on buffer pools is something called buffer pool bypass, which just says, all right, the query is going to have some local memory of its own that's not part of a buffer pool, and it will just store the pages that it gets from disk in that kind of in its own local memory rather than in the buffer pool. And this avoids basically taking over or flooding the buffer pool with a bunch of pages that maybe we only need to read once and we won't ever need again for this query. And so an optimization could be when we know that it's a page we just need to read once and then not care about, to bypass the buffer pool and put it in some other kind of memory. This works, of course. This is mainly appropriate for pages that we're only going to read and not going to write, because the buffer pool is part of what is managing persisting any changes we make to data in memory onto the disk. So also a strategy that that has come up before, this late materialization. You may remember from last time, we might have an operator do early materialization, fill out the full tuples and pass them up, or late materialization only includes some sort of reference or offset that indicates which tuples should be included in the result without actually going and fetching the data for the full tuples. And in particular, in a column store database, late materialization is going to be useful because in our peanut butter and jelly tables here, they may have many attributes in each of them, and what we need at the end of our query is just two: the brand of the peanut butter and the flavor of the jelly. And so doing this late materialization, where as we're handing off output up the query plan, we just hand out, oh, here are the record IDs of the tuples that we'll eventually want, or here are the offsets in the data files where you can find the attributes for these different tuples. And remember, our column store has our attributes separated out into their own pages. The full tuple is not actually together on disk. And so then when we finally get to the end of the query plan, we can just go and retrieve exactly the two attributes we need, and we don't spend a bunch of extra work kind of reconstructing tuples that we actually don't need according to this projection. So late materialization, good for our column store systems. And the last, well, I guess we've also talked about having clustered indexes, and from talking about it from the perspective of, okay, the index has an order, and this order is reflected in the data on disk. And for thinking about these accessor methods, if we have our data our data sorted in our heap files on disk, if those are clustered, if those are sorted, as would be the case for index clustering, but you wouldn't necessarily need an index. You would just sort the data on disk by some attribute. That could improve sequential scan, particularly a sequential scan that's doing some sort of filtering. Then if it's saying, all right, all need something that's type equals fruit, then the sequential scan knows that it should just jump right to the first thing that has the type fruit, and then can stop scanning once it hits something that doesn't have type fruit. But you may be wondering, well, how does it know, like, to jump to where there's type equal fruit? And there could be various ways to store this kind of metadata, but one particular one is something called zone maps. And so to show you what I mean, continuing with the food theme, let's say if we have a query, I want to select star from desserts. So I want tuples from the dessert table, but I want like big, serious, heavy-duty desserts, like desserts that are really going to knock your socks off. And so I say where calories greater than 600, mean business. And so let's say that our some particular page of data in our heap file for calories has data that looks like this. A zone map is a separate separate information that kind of contains summary information about the data within a particular page, typically. So this zone map would look something like it would have entries like the min of this data is 100, the max is 500, the sum is 1200, the count is 5, and there could be other information in there as well. But this means that when our sequential scan for this query of calories greater than 600 gets to the page, right, that this is our, I don't know, page 101, and this is our zone map for page 101, what our queries will do is that as they're scanning pages, they will first check the zone map before they go to scan the page. And for this particular query, it could check the zone map, see that the max is 500, and say, well, there is not any data in this page. There's not any tuples in this page that I will actually want, so I don't need to scan it at all. And so these zone maps are kind of, there might typically be some other spot on disk that stores the zone maps for a bunch of pages of data. And so the query would first go look up the zone map before going and scanning the page, and this might let you skip lots and lots of pages that you don't actually need to scan. The kind of fancy, I believe Postgres, for example, SQLite, they don't support zone maps, but kind of the fancy commercial systems do, and for certain kinds of workloads, these could definitely save a lot of disk I/O. So that's the sequential scan, and a number of different ways we might improve that. Databases will often use an index scan if an index is available, and this just means scanning through the entries in a particular index. And since an index often doesn't have full tuples, it has some particular search key or maybe kind of multiple attributes combined into a single search key. If, say, we have a query that only needs a particular attribute, and the pages for an index on that attribute are happen to be in memory, or because they're only storing that one attribute instead of the full tuples, there are many fewer pages to cover the whole table, then an index scan over that index, whether it's a hash index or a B+ tree index, will save on disk I/O compared to just going and scanning the data files. Another kind of interesting aspect of index scans is to consider, like, when is like the database management system the database system is going to decide when to do an index scan instead of a sequential scan, and this will depend on a number of aspects, like whether an index on the appropriate attributes exists. So it's going to depend on index attributes, the query attributes, and how those relate to each other. The attribute domain, kind of what is the range of values that a particular attribute might have. What predicates are involved in the query on these attributes, and other aspects of the index as well. And an example of what this would look like is, let's say that we have a query where we want to select tuples from our menu table, where the number of sides that the dish comes with is more than one. We like to have some variety in there, and where the type of meal is vegan. And so depending on the scenario, and we also have indexes on sides and type. So we have two different indexes, one on size, one on type, and there are kind of different scenarios we might consider for when we would use these different indexes. So we have kind of scenario one where there are so we have 100 tuples total, and scenario one is we have 99 dishes with multiple sides, and we have 2 vegan dishes. And scenario number 2 is that we have 99 vegan and 2 with our multiple sides. And so in scenario 1, doing an index scan on type is going to be a lot more useful than doing an index scan on sides. An index scan on sides is going to reduce our number of tuples from 100 to 99. And so it's really not doing much for us beside that's different from our sequential scan. if we scan on type, it's going to take us from 100 to 2 tuples. And so using the type index in this situation is going to kind of reduce the amount of work other parts of this query have to do. In our scenario 2, this flips because kind of the more selective index is our sides, and the one on type wouldn't do much for us. So this is if we could use a single index. The databases also support what are called multi-index scans. And so this is a scenario where if we have multiple indexes that are kind of relevant to our query, the database can scan both of them and then combine the results. So as a bit of an aside, one of the ways in which these results get combined, and in particular the way that they get combined in Postgres, is with what's called a bitmap scan. And this is kind of a concept that's been, this concept of a bitmap has been sort of floating around at the periphery of this course for a while, so I wanted to take a moment and explain what is a bitmap. And so this is a way to represent a, it's a way to maintain a data structure of some set of things that are kind of true or false, or are in the set or not, or are in one of two states. And the name bitmap comes from the fact that we have a bit array, meaning an array of bits of a single binary digit. And so it would be something like, if we have our bit array, and then associated with each entry in our bit array, we have some object, some record ID, kind of whatever it is that we're making a data structure over. So maybe A, B, C, D, E, F, and then our bitmap would say, all right, A, C, and D are present or meet some criteria. B, E, and F do not. And so this pattern 101101 of our bitmap, kind of using a compact amount of data, only a single bit for each element, is recording like for some set of things which are in and which are out. And so the reason this is relevant to a, I guess, broader point on bitmaps is that when we want to compactly represent, we have some set of things that in different states of our system or for different queries are going to we're going to want to represent some subset of them. Bitmaps are a very efficient way to do that because we'll only use a single bit for each member of the set. But the reason this is relevant to a multi-index scan is the following. Let's say we have our two indexes, B plus trees with some record IDs at the root. And we have another one over here. And let's say that we have our two criteria that we're applying to our sides and type index. So we want sides greater than 1. We want type equals vegan. And what we can do is we can scan both of our indexes and produce a bitmap for each of them, indicating which of the records met that criteria. So let's say that we have, if we had like tuples like 100 through tuples 100 through 200, then we'd have a bitmap of 100 entries, and one index scan would set the ones for those tuples that had sides greater than 1. Scan of type would have a separate bitmap that would set the ones for tuples where type is equal to b. And so one way to visualize this is this sides greater than 1 returns some set of record IDs that match in our using a bitmap that match this criteria, and our other index scan returns another set of record IDs representing using a bitmap that match that criteria, and then we just bitwise and the bits from our two bitmaps and get out the resulting a resulting bitmap that has ones just for those record IDs that were both included. We could do the intersection of the two, and then that's what gets output. If this was an OR instead of an AND, then we would do like a bitwise OR, a union of the record IDs that we found with our two index scans. And so we can use this idea of bitmaps to have an efficient implementation of this sort of multi-index scan situation. All right, so the last thing that I want to mention is I've basically only talked about kind of reading queries in these examples, haven't talked about updates or inserts. So for updates and inserts, in addition to updating or modifying the data file, they also need to update or modify the index that is, if any are present for that attribute. And one sort of amusing anecdote about that is that imagine that we have a query that is scanning through the sides and is for any we're updating our menu, anything that we're making our restaurant all about maximum sides. So we write a query that says, all right, anything that has something like update sides equals 4, rather update sides equals sides plus 1, where sides are less than 2. So this might not, I don't think that's perfect SQL, but gets the point across. We want to go through and update the sides attribute, add one more side where the sides are less than 2. And so imagine that we're scanning through our data, and that data is in an index, or it's clustered, and it's sorted on the number of sides. And when we update a record, from say we find a menu item that had 0 sides. All right, we're going to update it to have 1 side. Well, that's actually going to move it within the index, right? We're updating the index 2 from the place where it had 0 to where it's 1. And if we continue scanning through the index, we might encounter that same tuple again, and it's still less than 2. So we update it a second time, and it moves again, and we might encounter it again as we keep scanning. And this was actually a database bug that is referred to as the Halloween problem, not because it's spooky or you have tuples showing up multiple times, but literally because the researchers who first discovered this bug were working on it on Halloween when they discovered the problem, and they said, you know what, let's just give it a name. Today's Halloween, we'll call it the Halloween problem. And that has stuck. This is now the Halloween problem when you're updating tuples in an index. So with that, I'll bring the video to a close. I hope you're seeing how kind of these query plans are bringing together these different parts that we've been talking about. Now, I've been thinking over midterm break that every time I say something at the end of the video about your questions, bad things happen. And so I had an idea. What if I just escape before saying anything about questions? Then maybe the void won't get me. So I'm going to try that. Bye. What the?